Hi, hello and welcome to week 7 of Introduction to Programming, Einführung in die strukturierte Programmierung. As you can see, I'm alone today. Sebastian is unfortunately sick, but I think, I hope that I can also do it very interestingly for you. Today we have again a very, very important and interesting topic. We are talking about memory once again. Michi and Julia already did a great job and presented some very, very important topics. And we will now have a short look if you can remember it and understand it a bit. In the beginning, we will make a short quiz about the memory again. Then we will talk about enums, and our today most important topic is about data structures. So with data structures, we are now applying all our concepts we are knowing in a very important way, but we will see it later. In the beginning, as always, a few organizational methods, or in this case, I think it's just one slide. We will publish weekly exercises today, and they already belong to assignment 4. Because today is mainly about data structures, and data structures are a learning goal of the last assignment of assignment 4, which will be released in 2 weeks. So today is assignment 3. Don't get confused. Today, the lecture content and the weekly exercises already belong to the assignment 4 content. All right, then let's continue and start with a recap of heap and stack. So a short overview again. I hope that if you were in the practicals a few minutes ago, that you know that the difference between the stack and the heap, especially and the availability, variables are available at the stack until the end of the function, and variables are available at the heap until you free it. And when do we use it? So if you have a fixed size array, let's say you know that you have always 10 numbers, you can create it on the stack when you know you will only use it in this function. And on the other hand, if you have a dynamic size, let's say the user can input an arbitrary long text, then you should use the heap for that. And now let's start with the first question. So please join the quiz. It should work again with the QR code, or go to slido.com and enter this code. And the first question is, what code block is missing here inside the malloc? So the practicals already gave you, hopefully, a very, very important and a good hint for that. So there is one correct answer, when I can see it correctly. Yes, one correct answer to that. What do you think? So Julia did this wrong before, but I know that she knows it. So what's the result here, or what's the correct answer? Yeah, great. Julia, you did a great job because everybody knows it now. All right, so yeah, the correct answer is 10 times size of integer, and this works because we need 40 bytes, so 10 times 4, and the other solutions won't work because it does not, we do not get 40 bytes here. This won't work. Great. So again, another very important part of the heap is that the memory is available until you free it. When you have a function like our create array functions, where we talked about last week or 2 weeks ago, we create here an array, we always check for null, and then we can return now the array because it's on the heap. And what this does is it copies our pointer on the stack, which points to the heap back to the main function here. And this is very important because this is what Michi said before. The pointer to the array still lies on the stack. So the variable, the pointer, is still on the stack, but it points somewhere on the heap, and you can copy that. So when we go back, you see here, when we call this return, it just copies the pointer back to the main. Then we still have the same address, and we can access the array in this case. Next question. So when we shortly go back, then there is a free of this array. The free function automatically sets the pointer to null after releasing memory. Is that true or not? Okay, let's see what you say. It's wrong. Yeah, it's false because you have to set it to null. Free just deallocates the memory, so it does not belong to you anymore, but you still can access it. So in this case here, when your program is in this line, you still have a pointer to an array region or to the memory region on the heap, but it doesn't belong anymore to you. So what you should do always is set the pointer to null, because then, as Mich and Julia showed you before, when you still want to access it, you get at least a segmentation fault and the program crashes. But I have to admit, I should in some way correct Michael here, because he said it's a very, very good idea to have a segmentation fault, maybe during development, but not in your final version. So in your final version, segmentation faults are not the best idea. But during development, of course, it is better to have a segmentation fault than not seeing that you have a problem in your code. All right. We already talked also about the memory layout. We showed that there's a stack which grows down from the middle of the memory segment. We have the heap, the data segment, and the code. And what we also can do, and this is very, very interesting, you maybe know that we can print the address of a local variable, and we get something like this. Now you know you can also print the address of a heap array in this case, and this is something like this. It's lower, it's somewhere here. You can also print, in this case, the address of a constant, and you will see it's in the data segment because it's lower than the heap, but it's quite near to the heap, I would say. And what we also can do, and I think we will show it, I don't know if next week or in 2 weeks. In this case, we can also take the address of a function, and as we know, the code is also stored somewhere in the memory. So in this case, I can just write the address of my function here, and I get back an address, and this is where our code is stored in the code segment. We will talk about that later, but this is basically a so-called function pointer, where we just have a pointer to a function. All right, next question. I have a given code here, and also based on the knowledge now from the practicals, what could lead to problems here? Okay, let's go through it. We have an array with malloc, so 3 elements of integers. Then we ask, okay, if it's null, then return. Looks good so far. And then we access the memory at the location 0, 1, 2, write 1, 2, 3 inside. And then we want to have a bigger array. 3 is not enough. I want to store 5 elements. And I want to enlarge this array here to 5 elements. Ask again if I return null, and then, store 2 more elements there. What's the problem? What would you say? Yeah, great. The memory leak if realloc fails. So this is also what Michi and Julia showed you before. Let's have a look into that once more. When you have realloc like that, you have a pointer on the stack pointing to a heap location where the address or where the array is stored. We have here in this case, I don't know, any garbage values. There is again 1 garbage value. And this would be better when you store this grade in a temporary variable. Because when we do it like this, so we now take the temporary variable back from realloc, and we have written now 1, 2, 3 into this array. Next step, we use realloc, we hand over the new size. And as you can see now, our memory location has changed. So we switched from here down to here. Our grades still points to there, to this memory location. Our temp pointer points now to this memory location. If the temp would not, so if realloc would not work, if temp is null, then we should free this memory location up here and return, because then we have an error. But in this case, it worked. So we override then our temp with grades and say, okay, now both pointing to the same location here. And then we can, fill in our 2 remaining numbers. When we don't do that, and when we use something like this, so let's say we do not catch the return value from realloc here. As you can see, we just call realloc and say, make this bigger for me. We would still have a pointer to this memory location up here, but the memory location might have changed. So what we would do with these 2 lines of code here is we just override here memory or variables, addresses, whatever is stored there, which do not belong to our array. So because our pointer still thinks this is the first element, this is the second, the third, the fourth, and so on. So it still thinks that this is our array here, but our array was already delocated to, in this case, down there. So this is why it's very, very important, as you saw already in the practicals, always check for, take this pointer, check it for null, and then override your current pointer with the temp pointer, because then they are pointing to the same memory location. What I'm missing now is, because I run out of space here, but any ideas what I would miss here to make it even more perfect? I don't know who was fast it is. Sorry. Please. Yes, exactly. I should set the temporary pointer to null, because then I'm safe, and if I ever would work with the temporary pointer, I will get a segmentation fault. Exactly. All right. That was it already from our recap from memory. Any questions before we continue? Yes. This one. Yeah. Okay, very good question. Why don't you need this here, the address sign of the heap? Very, very good question. Let's turn it a bit around and let's see why we would need it at the other variables. So here we have an integer, and this is just an integer storing the value 4. Here I would need the address operator to get the address. The same applies for the constant. But the heap variable here is already a pointer, so it contains already an address. It is a pointer to somewhere else where the data is stored, and that's why you don't need it here, because it is already an address stored there. What you could do is, again, write here the address operator, but then you don't get the address of the array it's pointing to, but the address of this function. And then it will be, again, a stack address, because the pointer here is stored on the stack. Yes? Good question. So the question is, why do I not have to set the temporary pointer free? Or to free the temporary pointer, right? Let's look at this. Temp and grades point to the same memory location. So if you would write somewhere here free temp, it actually frees your array then. So it is really the same array both variables are pointing to. And if you would do it, you cannot work with the grades anymore, because it's basically the same array. It's just a reference to the same array. So you should set this temp to null, but not free the temp, because it's the same memory. It points to the same memory location on the heap, where also your grades are stored, and you want to work and continue to work with this array again. So when you would free this temp pointer here, and you then access grades on index 3 and grades on index 4, you will again get a vagrant error, read or write, in this case, write of invalid write, because you are accessing memory which you already freed. Any other questions? Okay, then let's continue with, at least in my opinion, a bit easier topic, and it's enums. Enums is a bit similar to constants. Let's call it like this. Let's say we have a bunch of constants, or in this case, we want to somehow define our weekdays, and what I could do is define Monday, Tuesday, Wednesday, because I want to write it like this in my program, but this is a lot to write and does not look very, very interesting here. What I can do is I can use an enum for that. Enum is just short version for enumeration, and you can kind of group constants that belong somehow together. So in this case, I can write enum, Monday, Tuesday, and so on. And what's behind is when you create it like this, you get automatically a value assigned like this. So the first element is always 0, the next is 1, and so on. And you can use it as it is a constant in your code. So when you write printf Tuesday, it will output 1 because it's 0, it's 1. This is the index, basically, from it, so the value of it. We can go further and set, for example, values for each individual enum elements. So we can say, okay, we want to start with 10, and then, as you can see here on the table on the right side, the next one is 11, Wednesday is 12, and so on. And I can do it for every arbitrary number I want to do. And again, then I can use it in my code as it is like a number. And why should I use it? Why just not writing the number? It's basically the same idea why you should use constant. It's just easier for programmers to read, especially when you read your program, let's say next year or in 5 years, or also a colleague of yours or your tutor reads the program. It's easier for us to know what you meant when there is like a text like Tuesday, instead that there is like 11. So printf 11 seems a bit random to me, but if there is a printf statement and if you want to print Tuesday, there is much more information for me, and I, as a tutor or as a colleague, know, okay, you have something in mind with days, so whatever, it belongs to the days here. And we can also set different values. So we can, for example, say the Monday should be 10, the Tuesday should be 2, and so on. And we can work with that as well. So as you can see, it's pretty much the same as a define. It's basically a constant, but it groups somehow, constants together that belongs together. So until now, we talked about enums without a tag. What we can do is pretty similar to structs now. We can write a tag here and give this enum a name. So we can say, okay, we call this enum weekdays. And similar to structs, we can also typedef them. So we can write typedef, and this is my existing data type. And in the end, I have my new data type. And the cool thing now is that I can use this again as my own data type. So I can say, okay, what's the current day? I create an object or a variable of type weekdays, and I call it, my variable name is current day, and I initialize it with Thursday, for example. And again, this is much more readable than I create an integer, call it current day, and initialize it with 3. Would work somehow, but this is much more readable because now I know, okay, it somehow belongs to days, and the cool thing is that you can still calculate with these values. So for example, we have a next day function here, and we have our weekday today, which is Thursday, and then I can hand over today to this function which takes a weekday, so this enum, I can increment this day and return it. So I'll get back tomorrow, and then I can print out tomorrow. The output is then 4. It's not the text. It would be very, very cool if the output then is Friday, for example. But unfortunately, this does not work in C. What you can do is write a switch case and then ask there if the output is 4, return the string Friday, for example. So it would be even better, I would admit, yeah, that when the output here, or when I used Thursday and I print it, the output should be Thursday or Friday. This does not work. You have to write it on your own to get like the text of it. But still, what you can do is you can calculate with it, and yeah, this is very, very useful, especially when you have a lot of constants that belong together. In this case, enums are very, very useful. For example, if you have many, many error codes in your assignments, you can kind of group them in an enum, and then you know all your errors or error names. So for example, you have an error name for the exit code 0, an error name for the exit code 1, and so on. Group them together into one enum, and then you can use it. All right, any questions to enums? Yes?
Would it be possible to make the enum values negative? For example, set Tuesday to 0 and Monday -1.
Yes, you can also, I don't know exactly what's the value range, to be honest, but you can also use negative numbers. I would suggest they are bound to integers 4-byte or long 8-byte. I don't know, but you can definitely use negative numbers too, yeah. Yes? You could use a char. So you mean you write it something like, where did I have it? Okay, get lost now, sorry. To write here a char somewhere at initializing. Yeah, it would work, but it still would name the ASCII number. So it would interpret it as ASCII value and take the number out of it. So if you write A, it's like, for example, 92, then the value, yeah. But I think it should work, yeah. Any other questions? Yes? That's a very, very good question. Julia, do you know that? Can you iterate over an enum? I know that it's possible in C++, I think, but I don't know if it's possible in C.
I mean, you can just take the highest and lowest element.
Yeah, yeah. So you can take the highest and lowest element and iterate over them when they are sorted like this. Then you could kind of iterate it because you just want to iterate from 10 to 16. But when you have values like this, they are like randomly, then it's not possible. No, I don't think it's possible then to iterate over it, yeah. So it's not like an array where they are stored next to each other. It's kind of like constants that you group mentally as a programmer, but you cannot really use it as an array. So if you want to iterate over it, I would highly recommend then using an array. All right, then let's come to our main topic. The advantages of enums, as I said before, it's very good to compress related numerical constants together. It very, very improves the readability, and it's type safe, so the variables can only take these predefined values, which is very cool. Okay, let's come to data structures. And this is a topic, as I said before, where we now can apply all our knowledge about heap and dynamic memory in general, pointers, and so on. So now it's getting very interesting because we can build our own data structures. And one data structure we already saw, I think it was in the first lecture, where we talked about this bookshelf. Bookshelf is kind of also like a data structure because it stores somehow data, in this case books. But what is a data structure in general? So, like, a kind of definition is it's a specified way to organize and store any kind of data. And you already know one data structure, at least one data structure, because you used it a lot already, especially in assignment 2. Any ideas? Yes? An array, yeah. Array is one data structure, and this is, yeah, maybe the most basic one or the easiest one. That's why we started with it. The array is just a continuous region of memory where you can store elements inside. You have an index, and you can iterate over it. You have a start and an end. This is, yeah, maybe the basic version of data structures. But there exist others. For example, a linked list. We will talk about linked lists today a lot, and I hopefully have also the time to program a bit a linked list, that you can see it. And as a short hint, you have to implement also a linked list in the third assignment. So that's why I would recommend to have a closer look into this topic of linked list in general and today, and also I think in the weekly exercises there is one topic about linked lists too, or at least one, I think 2, yeah. So a linked list is a bit different to an array. It always has an head and it has elements inside. Okay, that sounds pretty similar to an array, but the cool thing is that these individual elements here does not, or they do not have to be next to each other. They can be, I don't know, some is here, another element is here, another element is here. So you don't know where they are stored, and to have like this link between the individual elements, you have a data, and you always have like a reference where the next data is stored. Any ideas what reference this could be? Yes, a pointer, yeah. So in each element you have one additional variable which just say, oh, by the way, the next element is here. And there the next element is stored, you have the values there, and it again has one member, a pointer, which says, and the next element is stored there. So this is kind of cool, and it has a lot of advantages, and we will have a look into that today. There are many more. For example, a stack. A stack is, again, kind of an array, but with limited access. So at an array, you basically can iterate over it. You have access to all the elements. With a stack, you only can modify the top element. So it's not like vertical. It's, in this case, it's not horizontal, as you might know an array or imagine an array. In this case, it's vertical, and you can only access the top element. So what you can do is you can push on it, so just place another element on it, and pop. Pop means just taking the top element. But you cannot access the other elements down here, because when you, for example, want to access the A element, you have to pop and take all the elements down until you get and come to this A element. You might now ask, why should I use a stack when it's limited or more limited than an array? And sometimes it makes sense to limit yourself as a programmer. Maybe not for easy things like, I don't know, a program with 50 lines of code. But when you're in a company writing code with, I don't know, 20 to 15 other colleagues, and you know that you always just want to add one element to your data structure and take the last element added to it, then it would make sense to do it like that, because you limit all your colleagues also to do it only in this predefined way. So maybe you can imagine like there are some things in real world that works like a stack. When you play cards, for example, there is always a card stack. You can just take a card from top. You should not take a card from in the middle of this card stack. And maybe you could also like place something on it, but not place it somewhere in the middle. So sometimes it makes sense to use a stack. Another data structure is the so-called queue. A queue, or Warteschlange in German, is, as you would expect, you have, again, like an array, but you can only access the first and the last element, kind of, because you can take the first element, or if you want to add a new element, you have to add it in the end. So let's say you want to enter a bus, and there is already a queue of 5 people who want to go inside the bus. You most likely and hopefully queue at the end and do not go to the front and say, I want to be first inside. So you queue at the end, and the one who is in front of the queue can first enter the bus. So it is also inspired by real world, where you always or sometimes have a queue in many situations. And you can also have a data structure sometimes where you want to have like the first come, the first served, so a so-called FIFO. Maybe some of you have already known it. This is basically the implementation of it. Okay, one last data structure for today is the tree data structure. And this is kind of a bit more complicated, but there is, I think it still is in the 3rd semester, there is one dedicated lecture just about data structures. So this is kind of a first, I just want to show you a few data structures which exist, but there is one dedicated lecture for all kind of data structures. And the tree is also maybe a bit more advanced. And in a tree, you have a root node, and you again have links to others. A link is similar at the linked list, again, just a pointer. But in this case, you don't have just one link to something, you have 2 links. So for example, if this is, I don't know, an element, and it points to this element and to this element. They are both children, so B and C are children from A, and D and E are again children of B. So this is called the parent node, and the nodes down are called the child nodes. We will talk about trees next time, and Sebastian will show you also a short example about trees, how to implement that in C. So why are there different data structures in general? Why not just use an array all the time? It's depending on your use case. So depending on what you want to do and what you want to implement, a specific data structure is better suitable. So as I said before, let's assume we have our card stack. Maybe a stack is more suitable than an array. And it depends on how often do you read, write, delete something. What's the size? How many elements do you have in your data structure? How often do you want to read, write, whatever? So depending on all these different use cases and how you use your data structure, also different data structures are suitable. So for example, let's go back to the array, and let's say we want to delete an element from an array. Maybe you already encountered that problem. you have this array here and you want to delete now this element at index 1. So when you delete it, and I mean now really delete it, not just set it to 0, I just want to delete it, which means that, okay, I had to move now my next element to index 1, so index 2 moves to index 1, index 3 moves to index 2, index 4 moves to index 3, and also 5 moves to index 4. And then I have to clear the last element because I want to have it in one region next to each other. So that's a lot of operations for just deleting one element. So maybe now you can see that an array for these kind of data structures can be annoying and can take a very, very long time. So if you now know that you will always or very, very often delete elements from your array, you always have to do all these operations. Maybe the array is not the right choice for this implementation. Is this clear? Because if you have questions to this, ask it now. It's very, very important that you understand that there are different advantages and disadvantages of arrays, for example, or linked lists or whatever. Great. So this is most likely not the best choice for a problem or any implementation we have. Let's go to linked list and show the advantages and also some disadvantages, the pros and cons from linked lists. And I want to show it with kind of visualization. Maybe some of you also have that. This is actually Sebastian's top playlist from, I don't think it's Spotify, no, but it's his playlist, yeah? And you can see here now there are different songs inside. In this case, there are more than 3, but just as an overview. So we want to now code a linked list, but before we want to code a linked list, I want to show you how it works in general. So I have here one element, one track in this case. The track has an artist, it has a track. It has more additional information, but when we want to now implement it, we just want to talk about the artist, for example, the title and the length of a song. This is sufficient for now. So when we want to implement it, we can create a struct, artist, title, length inside. Let's say the artist cannot be longer than 50 characters, the title too. And I will now visualize this in the next slides like this. So it's basically just another representation of this struct here. We have an artist, and this is the value, and this is the address of this whole struct here. What we additionally do have is, when we have a playlist, of course we could store it in an array, so they belong somehow together, these individual songs. But what we want to do is we want to link them using a linked list. So we additionally need a pointer to the next song. So what we do now is, when we have our struct here, we create another member variable that says it's a pointer. We call it next song. And that's very important now. The data type is struct. So it's basically the same here, struct underline, song underline. So this here must match this here. You cannot write song pointer, so this data type here, song pointer, next song, Any ideas why? Why don't you can write here song pointer next song? Yes. Exactly. It's in the declaration of a song. Basically, we are declaring the song here, so we cannot use it the line before. But what we can is, we can use this term here, so these two terms here, as a data type. From now on, so from this line of code here down, we can use song as data type, but inside we have to use this data type here. And this is a very, very common pitfall at the exams, because people struggling with getting the right data type here, because they always try to just use song here, but here it does not work. That's why I want to point it out again. Here you have to write struct underline song struct pointer, because this is the data type here. Another question, do I need a pointer here? What would happen if I don't write the pointer asterisk here? Yes?
And you would create another struct in a struct.
Yes, I would create another struct in a struct. How big is my struct? How big in general is a struct? So the size of a struct is always just the sum of its members. So if I have a struct with an integer, which is 4 byte, the struct is also 4 byte. When I have, in this case, I have an artist with 50, a title with 50, and a short, which is 2 byte. So I have 102 bytes, and I have a pointer, which is 8 byte. So altogether, my struct element has 110 bytes. When I don't have this pointer star here, it's creating a new struct element, which again contains a next struct element, and again contains a next struct element. So you cannot create an element like this. I also have it in my code here, so I hope you can see it. Is it big enough? Yeah. Okay. So when I write it like this, you will see this does not work, because it's not a pointer and it cannot determine how big this struct is, because this is again one whole struct, which again contains another whole struct, which again contains another whole struct, and so on. So it's getting arbitrary big, and this does not work. So that's why you always have to use pointers inside to point to the same, to an element with the same data type. Okay, so another thing is we have to set this next song to null in the beginning, or at least the last element has to be null. When we have more songs, let's say we have now 2 songs. The first song is my Bob Dylan song, and then it has a pointer to the next song, and the address is then just the address of my next song. And again, this has a next song which points to null because it's the last element in my linked list. Okay, let's go through the most important list operations, so the linked list operations we can do now. Let's say we have these two songs here, and the first one points then to the next song. When we want to iterate over it, so iteration just means go over all the elements, In arrays, it's pretty simple because we just increment our index, and then we have the next element. In this case, it's a bit more complicated because we want to iterate until we find the last element which points to null and next. So what we can do is we set a pointer and call it current. In this case, let's assume we have here this struct element and we just take the pointer out of it. So it's just an address to this first element. And what we can do now is we write current next song and write that into current. So when I execute this, my current pointer will then just come to this song. And when I execute it once more, my current pointer will then point to null because it always goes this path. Okay, at first I go this path, then I have a look at this, okay, then it points to null. So this is how I can iterate over a linked list. Let's say we have one function doing that, so this just gets the head of the playlist. The head is always the beginning of my linked list. So at first I get the pointer, so they are pointing to the same address. And what you usually do is you write a while function, and this while function runs until the current, so this pointer is equal to 0, also to null. So as long as current is not null, you can do something, for example, print it. We will implement that. I hope we have time for it. Yes, it should work. So we'll implement that and also have a look into that. Another important function is the add function. So adding a new element at the end of the linked list. So let's say we want to add a song to our playlist. How can we add that? Okay, so let's say we are in, it's nearly Christmas and I want to add the perfect Christmas song most of you maybe hate. I also hate it, but it's Christmas time, so why not? And we want to add this Last Christmas song to our playlist. So what we do is we have our current pointer, then we jump to iterate to the last element in our playlist. We have now the last element, and then just add here the next song, the address of my next song, and set this to null. So we just add one element in the end, and this is how we can add new things to our playlist. This looks easy. The implementation in C is unfortunately not that easy, but that's why we will have a look into it. Okay, any questions about the theory of, linked lists, adding, iteration in general? Then let's go to the implementation. This is, it should work. So this is like a skeleton I have. This is our song. And you can see here I have the artist here, I have the title here, the length, and a pointer to the next song. And first what I want to do is I want to create a function that just creates a song for me and then returns it. So let's try void create song. And what should be inside of that? Okay, let's break it down. We want to create a song on the heap, first step. Second step, we want to set the members, so artists and so on. Okay, we need the artist, so that's a char pointer. We need the title, and we need the length. This is the place where I want to set it here. And then I want to return my new song. So this is basically what the function should do. Okay, let's create a song on the heap. We create a song pointer because we know when we create it on the heap, we're using malloc. So let's call it new song. We use malloc with, what should I write now? How much memory do we need? Yeah. The whole struct, yeah? So how can I get the size of the whole struct? Size of, yeah, and then? Sorry, once again? The size in the brackets. I don't know what you mean. So, like this. Okay. Do we need a pointer here? No. Why not? Yeah, we want to create it for the whole struct. That's again a very, very common pitfall. People want to reserve memory for a pointer. As you might know, a pointer is always 8 byte. We need more than 8 byte, so we would allocate to less memory if we just use here size of song pointer. So, okay, now it works. I allocated memory. I always have to check for null, of course. So if it returns null, in this case, let's say return null again. Okay, I need a return type. Of course, I want to return the song. That's why it makes sense to return a pointer to this new created song. The next step, I want to set the members. Okay, let's say new song artist is equal to artist. Does this work? It's already, give me a hint, it's not assignable. Oh, yes. No, this is also wrong because this is a pointer, so we have to dereference it first and then access the member, and this arrow, what we saw before, is the same. It dereferences the new song and then access the member. So this is correct. This is tricky, and it's also, today I talk a lot about pitfalls, and all these pitfalls are pitfalls you might encounter also in the exams. This is a problem because you're actually writing a pointer, so this artist here is just a pointer, you're writing a pointer into an array. Does not work. What do we need here instead? How can I get a text which is stored here in this artist variable, and I somehow want to copy it to this array? Dereference it, okay. Dereference, I will get the first element. So I will basically get the first character. Yeah? No. fgetS is also wrong. What I need to do is, I need to use, so what I basically want to do is I want to copy each character of this character array, want to copy each character into my artist array, and therefore there is a strucopy function. So you have to use strucopy, and what this does is it copies all the characters from my tab pointer here and copies all to my new song artist, so basically into this array here. So when I want to call this function, let's just try to call it. I get back a song, let's call it S1, create song, and then I want to say, okay, what's the name of it? It was Bob Dylan. That's the first argument because that's the artist. The second one is like a rolling stone, and the third one is the length. So this is how I call it. And then I get here the artist, the title, and the length. So I want to set the artist here. I want to do the same for the title. So I just copy all the title. And I want to say the new song length is length. This works now because it's just an integer, or in this case it's a short integer with 2 bytes. But this works because here I can just assign a number to another variable. But if you have an array like these two, you have to use strcpy, strncopy, memcopy, whatever. Yeah.
Is this the same as if you do a for loop and get char?
Getchar will read something from example standard input. It's the same as you write your own function that takes 2 arrays, this array here and this array, and just copy all the characters from the second to the first array. This is basically what strcpy does. It's also just one while loop, for example, to go through all over the elements, all characters, and copy them into the other ones. So it's what the name says, it copies the string from a given source to a destination. Okay, what I also want to do now is new song next is null, because I have to set it to null, because I always want to have, like, at least my last element should be null. That's important. So when I have to create song for now, let's set this next to null so it does not point to somewhere. And in the end, I want to return my new song. Great. That should work. Let's test this and write a function, a print function, to iterate over it. So let's say we have another song in our playlist, and this one was, so just give it a name and a title, Humpty Dumpty. It's interesting what Sebastian is listening to. And now I want to link them, because currently I just have 2 elements, but they're not linked together. So I have this element, I have this element, but this link is missing. So what I need is S1 next is equal to, what do I need here? So again, this is my S1, this is my S2, and I want to set my next to like the address of the next song. So what I can do is just writing S2, because S2 is the pointer to this element on the heap. Now I've linked it together, and let's write a function called print songs, which takes the head song, and now I want to iterate over it. So I will start with the first one and output the artist and the title, and then the same with the second one, and go through all the elements I have in my linked list. So what I do is, okay, before that, I write like an iterator or just write current in this case. So now I have my head, which is pointing to the first element, and I just created another pointer which also points to this first element here, because this is the one I want to change. I want to iterate over all the elements. So I can write while current is not null, then printf. Okay, I will copy that from the solution because it's a lot to write, I think. Yeah, so what this basically does is it prints the artist, prints the title, and prints the length. Okay, let's try it out. So print song, and what should I hand over to this print songs function? It requires the head, so the first element in the linked list. What's the first element in this linked list? We created here 2 elements, so you have a 50-50 chance basically. S1, yeah. S1. Okay, let's execute it. Oh, this does not look good. It's basically an infinite loop. Any ideas why? Problem is here. Yes? We never go to the next song. Yeah, this while loop goes until current is not equal to null. It never gets null because we're always printing the first song. So what we need is current is equal to current next. So this is what we saw here when we go over and over the next element. So basically this operation here. When we print it now, where is it? Yeah, let's do it again. It works. So the first song, the second song, this looks good. Okay, so this is basically what you need when you want to iterate over a linked list. It's not that complicated. We only have 5 minutes time, so I think we will hurry up a bit and go back to the slides. Okay, I missed a lot now, of course. So I created 2 songs, and these 2 songs are not freed currently. So of course we have to free it here. Yeah, I don't want to do it now, but it basically works the same. I would just write a function which iterates over all elements and just call free for each element until we reach null, which then marks the last element in our linked list. I want to add one more thing here, because in this create song, I also want now, when I create a song, that it adds the song in the end of my linked list. So when I create a song, I don't want to link it manually like this. I just want to create a song, and it should be linked automatically in the end to the end of the linked list. So what I can do now here is I can modify this. So I create a song, that works good, all good. But before returning it, I want to find the end of the linked list and add it there. So what I need is the head of the song, or the head of the playlist, so the head of this linked list. And again, I want to iterate over it. So let's iterate over it. So I just copy it and remove this here now. So I take again the head, iterate over it, but I want to stop when I'm on the last element. This iteration here runs until I am basically here after the last element, because it first gets to this one, then gets to this one, then gets to this one, and then it goes to null, so basically this case here. And what we want to do is, on the last element, we want to modify this value null here and set it to the next, which we just created. So how can we stop at the last element? Any ideas? Yeah. Current next is not null. Exactly, yeah. This will stop when I am here, because it stops when I'm at the last element and the last element points to null. Great, and what I can do now is, so in this line of code here, I always know that current is now my last element. So what I can do now is current next is my new song I just created up there. And that's it. That's it. So this is basically what I can do when I add it at the end. And the only modification I need here is that I have to give the head or hand over the head as first parameter. Usually, so in this case, it's easier because the head is my S1. In the first case, it's not that easy because I don't have a head because I'm just creating the first element. So what I would need is when I hand over null here, so null means, okay, there is no head. I cannot give you a head now. There is no head. So please create a head on your own. So there you need another case here. If the head is null, then, what should we do now? Then we should just return my new song. Because in this case, I don't need to iterate over it. I just want to return my new song. And this is going to be my new head. So this will be my head. I can remove this, by the way. This will be my head. And so in this case, I come to my head. Okay, head is null in the first place. This works, so it just creates my new song. So I'll get here my head. And in the next iteration here, I hand over my head and I will add it at the end. I don't have time to show you more. I just wanted to show you more, to be honest, but I don't have time for that. Just give me 3 more minutes because you will need it for the weekly exercises and also for assignment 4. So this is all what we already saw. Another thing what's very important, and this is what you should use or have to implement at the weekly exercises, is a remove function. So deleting something from a linked list. Deleting from a linked list is very easy compared to deleting something from an array. We saw before deleting from an array is very, very hard because you have to move all the values afterwards. This is very easy because you have to iterate over it again, and you have in this case one song here in the middle you want to remove. And the only thing you want to do is you have to, add this next song, which should not point to this song anymore, but just leave it out and it should point to my third element. That's basically it, what you should do. So you have to remember your current you want to delete. You have to remember what's my previous, and just set on my previous next song is not this one, but it's my last Christmas song. So this is basically what you should do when you remove something from a linked list, and it's so much easier. The only thing you have to consider, of course, you have to also then free this struct. But that's basically it. Removing something from a linked list is, compared to an array, so much easier. So when you have a data structure which you know you're always removing elements, linked lists is a very, very good choice for that. So this is then the result of it. Removing the head can be trickier, a bit trickier, because you are deleting the first element. But it's not that tricky. The only thing you have to do is you have to move your head to the next element. That's it. And again, you have to free the first element, of course. All right. Yeah, we don't have time for implementing this, but as I said, it's your task in the weekly exercises to implement this remove function from a linked list. And it's the same example I showed you today. The same example is in the weekly exercise with this create song, with this add song, and so on. And there you should implement the remove function. All right, so to sum it up, linked list advantage is the dynamic size. You can effectively insert and delete. The disadvantage is it's sometimes a bit complex to implement and sometimes for you a bit harder to access it because you have to iterate over it. But yeah, this is basically linked lists, and next week we will talk about binary trees. So thank you for being here. Sorry for delay and have a nice evening.